Hello physics students, this is Mr. Dillick. Welcome to video 1 for our physics class. This is about motion in one dimension. Most of these videos are going to be about 10, maybe 15 minutes long. This first one is a little bit longer than the average video because it is introduction to all of the physics stuff that we're going to use for the whole year. So try and go ahead and bear with me with the extra length. So pretty much when we talk about motion in one dimension, that pretty much falls into two categories early on for us: linear motion and nonlinear motion. When we talk about linear motion, we're talking about objects that are moving in a straight line. That is, we're talking about objects that are going to be moving along a number line. And so we tend to think of motion in one dimension as motion along a number line. Nonlinear motion, on the other hand, is going to be motion in more than one dimension. It's going to be curved motion. And so there we're not really going to be thinking about number lines as much as we're going to be thinking about motion along a plane, or maybe even motion along a three-dimensional area, a volume. So to keep it simple early on here, let's just think about number lines. You learned about number lines early on in elementary school, and we know that a number line starts at 0. It can have a positive direction and a negative direction. That is, in physics, directions can be positives or negatives. Either one of those could mean direction. And so when we think about motion along a number line in physics, we really are dealing with 4 different number lines that you might be interested in. 3 of those number lines we might use as dimensions of space. So we have a number line that runs left and right, and that's generally called the horizontal number line, or it's called x, the x-axis. You're going to hear me refer to it as the x direction. And generally speaking, that's going to be left and right. Then there's a vertical axis, also known as the y-axis, and that's another number line that represents things moving up and down. And then there's another axis called the linear axis, or it's sometimes called the z-axis, and that would be things moving in and out, or more usually we often call that forward and back. Plus, time itself can also be put on a number line. It's a little weird because we tend to think of time as not having a direction, but it really does. We have forward in time and we have looking backward in time. Although we can only move in one dimension, we can only move forward in time, we can look forward or look backward. Whereas in the 3 dimension of space, not only can we look left and right, up and down, front and back, we can actually move in all of those directions. So the key thing to keep in mind about motion is that it depends on a frame of reference. We use these standard number lines kind of as a mathematical frame of reference for describing motion. Number lines give us 2 pieces of information. They tell us a magnitude, and the magnitude is always going to refer to an amount, how much, a quantity. It's the number on the number line. Whereas the direction we're going to use as a sign. Early on, directions are going to be positives or negatives. Later on, we'll use angles and compass directions and other things like that. But early on, let's just stick to plus and minus. So one of the directions on the 3 frames of reference is going to be considered positive, and one of them is going to be considered negative. So in general, to the right is considered positive, to the left is considered negative. Up is considered positive, down is considered negative. Forward is considered positive, backward is considered negative. Sometimes those are in and out. So into the paper or into the board would be considered positive. Out of the paper or coming out of the board would be considered negative. Now don't confuse a frame of reference with a point of reference. The frame of reference actually represents the entire number line. The point of reference is a specific position on that number line. And so we would pick some object to be our point of reference, and we would make that 0 on our number line. So in the case of our x-axis, we said that positive direction is to the right and the negative direction is to the left. So when we look at the x-axis number line, 0 would be if you were located right at that point of reference, some physical object that you're saying, hey, that stapler is going to be my point of reference, or hey, that wall over there is going to be my point of reference. And if you were found to the left of that, you would be on the negative part of the number line. So you might be 2 meters to the left of the stapler, and you would have a position of -2 on the number line. If you were to the right, maybe 3 meters to the right of the stapler, if that's your point of reference, then you would have a position of +3. And so we use a point of reference as an actual stationary object that we're basing all of the rest of our numbers on the number line, the magnitudes on our number line, are based on that object being 0 on the number line. Now, often the point of reference is also the origin. It's simplistic. It's simple for us to say, hey, let's go ahead and make our starting point also the point of reference. And a lot of times we do that in physics. But in this case, I think you have to be careful. Something could be moving and it started out already to the left or already to the right, above or below, in front of or behind the point of reference. And so the origin really is a position on that number line that represents the starting point. And it could very well be the frame of reference, but it's not always the point of reference, but it's not always the point of reference. Now, what we've been talking about here, for instance, when I mentioned position on a number line, these are what we call physics quantities. When something is quantified or quantitative, it means we can put a number with it. If something is qualitative or it's qualified, we're just describing it with a quality, but not necessarily a number. So we might say something's moving at 55 miles an hour. That's quantitative. We might say something is moving fast. That's qualitative. And so these are basic ideas in physics. We're going to talk about tons of physics quantities. So we're going to talk about force. We're going to talk about momentum. We're going to talk about how much energy it has. We're going to talk about what position it's at and how fast it's going. All of these are numbers that are measured. These are all things that are measured with a number, and so we call them physics quantities. Some of these quantities are basic. If they can only be measured and never be calculated with an equation, if it's just something, the only way you can get that number is to actually use a tool to measure it, then it's a basic quantity. If it can be derived, then it is considered a derived quantity. So take speed, for example. We could use a radar detector to measure how fast something's going. We could use a tool. But we could also use an equation, and there's a pretty famous one that says speed is distance over time. So if you can use an equation, then it's a derived quantity. It's derived from two things, distance and time. So what about distance? Can we measure distance, or can we actually use an equation to calculate distance? Well, as it turns out, there's no equation for distance. You have to get out a ruler or a meter stick or something to measure distance. So it's what we call a basic quantity. A lot of derived quantities are rates, that are things that are compared to time. So if we compare distance to time, or force to time, or momentum to time, if we take something and we compare it to how much time it takes to do it, that's considered a rate. And a lot of times rates are pretty important to us in physics. The most basic quantities we're going to be dealing with in this first unit are position. So that'd be your actual location on the number line. The only way to know it is to actually measure it. Time. We don't really have an equation for time, but we do have tools that we can use to measure time, such as a stopwatch or a sundial. And then mass. Mass is another one that we can measure, but not really use an equation to calculate. And so the mass that something has can only be found by putting it on a balance, for instance. So these are basic quantities. Now, a lot of these quantities are what we consider scalar. That is, they have a magnitude only, but we don't generally use an equation, a direction for them. Vector quantities, on the other hand, require a magnitude and a direction. So, for instance, your mass is considered scalar. When you get on a scale in the morning, you want to see how much you weigh. That's not exactly a measure of your mass. It's really a measure of your weight. And those aren't exactly the same thing. But let's just say you got on a scale to measure your mass in grams. Well, if you did that, you wouldn't get on the scale and say, oh, I weigh 150 kilograms east. That wouldn't make any sense because it's a scalar quantity. We wouldn't include a direction for something like that. But velocity, on the other hand, how fast you're going, might be something where you say, I'm going 55 miles an hour north. And that fact that you're including a direction makes it a vector. So a good example of a scalar quantity is distance. Distance is measured by calculating the total change in position of an object without accounting for direction. So we might take 1, 2, 3, 4 steps in this direction and then turn and take 5, 6, 7, 8 steps in this direction. Altogether, our distance traveled was 8 steps, and the fact that we changed direction is irrelevant. We just want to know how many steps you took, and that's your distance. Displacement, on the other hand, you have to picture moving on a number line. If something started out at 1 on the number line, for instance, and then it moved in the positive direction, so we went to 2, and then 3, and then 4, and then we stopped and changed direction, went back to 2, and back to 1, and back to 0. Now our displacement is going to be a little different than our distance because we actually started at 1, took a couple steps in one direction, a couple steps in the other direction. So our distance is going to include a lot of steps, but our displacement in this case is going to include just a change in our position. So we started at 1, we ended at 0, so our displacement is going to be 1 step to the left, or -1. That's different than our displacement in this case. So another important skill that we want to make sure we cover in physics is how to read an equation. After all, physics is really mostly about relationships. And so I just want to have a brief slide in here to talk a little bit about how do we know what the relationships are between variables when we look at an equation. For instance, I mentioned in an equation earlier, speed equals distance over time. How do we know what the relationship between speed and distance is? How do we know what the relationship between time and distance is, or speed and time? Well, those relationships are really going to fall into 3 categories. Either they're directly related, they're indirectly related, or they're not related at all. And when we look at an equation, we can easily tell how different variables are related. Pretty much, when I look at an equation, and I just put a fake one here, A equals B over C. If I said to you, hey, how are A and B related? Well, they're actually directly related, and I can tell right away just by looking at the equation because they're on opposite sides of an equal sign, and they're both found in the numerator of the respective fractions that they're in. So A is really A over 1, it's in the numerator, and B is in the numerator over C, which is in the denominator. So since A and B are separated by an equal sign, and they're both in the numerator, they're going to be directly related every time. Equally, if they were both in the denominator, they would be directly related as well. And what do we mean by directly related? It means that all other things being equal, if B increases, so is A. It's going to increase. If B decreases, then so is A. On the other hand, A and C are indirectly related because one of them is in the numerator and the other one's in the denominator of their respective fractions. And whenever that happens, you're going to have 2 variables that are indirectly related. So if one increases, the other decreases, and vice versa. Now later on we'll talk about the difference between linear relationships and nonlinear relationships, and that has more to do with graphing. But for now, what I want you to understand is that if they are not on opposite sides of the equal sign, like B and C, then you have to use some algebra to rearrange them to get them on opposite sides of an equal sign, and then you can use those simple rules. If they're both in the denominator or they're both in the numerator, then they're going to be directly related. If one of them's in the denominator and the other one's in the numerator, they're indirectly related. So I just want to take a moment to talk about symbols and base units. In physics, we use a lot of variables, letters, to represent certain things. And I don't want you to get the units confused with the symbols for the physics quantities. The basic system of measurement that most physicists agreed upon is the metric system. So when we think about, for instance, what is mass measured in, well, the metric version of mass, we're going to use the symbol M for mass, and we're going to use kilograms as the standard unit. And you should really memorize what the standard units are. But imagine if you were trying to think about M standing for mass, or maybe it stands for meters. Well, in one of those cases, M is the symbol for the quantity. In the other case, M is the abbreviation for a unit. And you got to make sure that you keep those separate. Please notice that position can have X, Y, or Z as its symbol, and it depends on the frame of reference. If it's left and right, you're going to use X. If it's up and down, you're going to use Y. And if it's forward and back, you're going to use Z. Here's our first physics equation, and in this equation, we're using an equation to describe displacement. You can see that funny triangle-looking symbol. That's the Greek letter delta, and that always means change in physics. And then we use superscripts and subscripts a lot of times with variables to describe something else. So in this case, X means position on a number line that is going left and right, and XF means final position, XI means initial position, and those subscripts tell us something specific. A lot of times we'll put a bar over top of a variable, and that might mean something as well. Like that happens to mean average. And so look for different symbols to mean different things. Remember, displacement is a vector, and we talked about this. Don't forget, you really need to memorize these conventions, that the positive directions are considered to be right, up, and forward, and the negative directions are considered to be left, down, and backward.